Now we shall have a look at Widrow learning rule. Having seen Hebbian learning rule, perceptron learning rule and delta learning rule, we proceed with the next learning rule, which is again a supervised learning rule, and it is independent of an activation function of the neuron. Hebbian learning rule could be used with any activation function. A perceptron learning rule could be used only with discrete, that is bipolar or unipolar, that is signum functions, and the delta learning rule could only be used for continuous functions, that is sigmoidal functions. Now here it can be any activation function of the neuron, but the activation function plays no role in the weight update. So that is the reason it is called as independent of the activation function. So, or we could also assume that it uses a linear activation function, and in linear activation function we know that f of net is equal to net. This rule tries to minimize the squared error between the desired output di and the neuron's activation value net of I, and net I is nothing but wi transpose x. So rather than the previous one, that is your continuous the delta learning rule or discrete perceptron learning rule, both of them would try to reduce the error, that was the difference between di and oi. But here it is trying to check and reduce the difference between di and net of I and not oi. So that is the reason it is called as LMS rule, that is least mean square learning rule. So it just even delta learning rule was trying to reduce the error, mean square error. Similarly, Widrow learning rule is also trying to do the same, but Widrow learning rule is given this name as least mean square learning rule. So the learning signal R is equal to di minus oi. And what is oi here? Oi is nothing but f net of I, and f net I is nothing but net I, because it is a linear activation function, and I have written it in terms of wi transpose x. So what is the weight adjustment? We usually have three things which are multiplied. The learning signal, that is R, is multiplied with a learning constant and then with the input vector. So here this di minus oi is nothing but the learning signal, and here it is replaced with nothing but wi transpose x. So you can write it as net of I also. And then yes, you need to multiply with the input signal, that is your input vector x. Now in delta learning rule we have seen that it uses a unipolar or bipolar sigmoidal function, and f net is also used, as well as f net dash is also used. So if at all that f net which was used in delta learning rule, if at all it is identity function, then f of net is equal to net. And what will be the derivative? Because it is net, the derivative f net dash will be nothing but 1. So what happens is that the delta rule equation, if at all we see, this is f net. So this f net will become equal to net, and f net dash, this one will become 1, and the delta learning rule finally reduces to the Widrow learning rule. So I can say that Widrow learning rule is a special case of a delta learning rule with a identity function. So you can say it in both ways, that is Widrow learning rule is a special case of delta learning rule, or you can say that delta learning rule can be modified for an identity function, and that will become the Widrow learning rule. So in both ways you can say this. Now the weights in case of Widrow learning rule are initialized at any values. So there is no specific rule say that particular weight should be taken. Any weights can be considered at the beginning. So now we have to solve some problems on Widrow-Hoff learning rule, and then we shall move on to the next learning rule.